Chapter 18, Section 4 introduces a very useful and important circuit called the differential amplifier. The differential amplifier will amplify the difference between two input voltages by a gain amount determined by the resistors in the circuit. So here I'm showing a circuit. It looks like it's only got one input voltage V in, but in reality we can say that this is one of the voltages, which is V plus, and the other one is V minus. And then the difference between the two voltages is just V plus subtract V minus. The gain factor is determined by the resistors. And to figure out the gain, what you do is you take one of the feedback resistors and you divide it by one of the input resistors. So the gain would be RF over Rin. Now there's a special case here that this only works if the feedback resistors are the same value and the input resistors are the same value. So here I have RF1, it's 10K. This is only going to work if RF2 is also 10K. Rn1 is 1K, and the gain calculation will only work if Rn2 is also 1K. So if you have this case then the gain is going to be minus Rf over Rin, which will be minus 10K over 1K, which is minus 10 in this circuit here. Put some values down here. Say this is 2 volts and this is 1 volt. The output of this, and here's the output formula here. V out is the gain factor multiplied by the difference between the two input voltages. So we would say that it's minus 10 times 2 volts minus 1 volt, and 2 minus 1 is 1 volt, minus 10 times 1 volt. The output of this should be minus 10 volts. Let's do the same example with the feedback resistors, but now let's make the input voltages, instead of being 9 and 8, let's make them 7 volts and 6 volts. So again, V out, which would be minus 10 times 7 minus 6. This would be 1 volt. So we would get minus 10 volts out again. So what I'm trying to emphasize here is that the absolute value of the voltages doesn't matter. Doesn't matter if it's 9 and 8 or 7 and 6. It's the difference between the two input voltages that really matters. That's what gets amplified. Let's try another one. Let's try 3 and 2. Well, that would be minus 10. Three minus 2, that would be again 1 volt difference, minus 10 out. What if it was a negative voltage? What if it was minus 2 and minus 3? What would the output voltage be then? So formula again, the positive voltage, which is what we're saying is the voltage on the positive terminal, it's the one that's more positive than the other one. So they can be negative voltages, but it's the most positive voltage on the inputs. So that would be minus 2 minus 3, which becomes minus 2 plus 3, which becomes 1 volt. So the difference between them is 1 volt, where Vn plus is higher than Vn minus. So you would still get minus 10 volts out. And then we can also do an example with, let's say, minus 3 volts on the positive and minus 2 volts on the negative input. So now the Vn plus is more negative than the minus one. What would that work out to? So let's get rid of these values here. So we would have the output is minus 10 times V plus, which was minus 3 volts, and we would subtract minus 2 volts. So that would be minus 3 plus 2. So the difference between the input voltages would be minus 1 volt. And that's what would get multiplied by minus 10 times. And so you would have minus 10 times minus 1 volt. So now your output would be positive 10 volts. So if the Vn plus is more negative than the Vn minus, the difference between the two input voltages would be minus 1 volt. and you would get a positive voltage out of it. So let's look at the other important characteristics of an amplifier like Z in and Z out. So Z in would be the impedance looking into the amplifier. And in order to determine that, what you have to remember is that if you have an amplifier circuit with proper feedback and it's at a stable point, the voltages on the two terminals of the op amp are the same value. So V minus and V plus, which is these voltages here on the inputs of the op amp, these 2 points are the same voltage. So we can say that they're connected by a virtual short. So then for Z in, what we would do is we would look into the op amp circuit and we'd say, what's the impedance between these 2 points? And you would basically look in there and say, here's my loop. So it becomes Rn1 plus Rn2. It's just the 2 input resistors in series. And they're in series because they're connected by a virtual short. So Z in equals 2 times Rn. And what about Z out? Now Z out is the impedance looking into the output of an op amp. And again, if it's a stable operating point with the feedback applied correctly, then the output adjusts until the inputs are equal, which as long as you're within the range of operation, Z out will be approximately 0 ohms. It'll adjust the output to get the right output voltage, and this is essentially a 0 ohms Z out. Another thing that you need to know about the differential amplifier is that it can be drawn in one of 2 different ways, and that the polarity of the gain is dependent on how you draw it. The magnitude of the gain will remain the same. The gain magnitude will always be one of these resistors divided by one of these resistors. So in the case of both of these, the gain on both of these is 10. In this top one, it's minus 10, and in this bottom one, it's plus 10. The difference in how they're drawn is that in this top one, the inverting terminal is shown at the top of the op amp, and the non-inverting terminal is shown at the bottom. And this enables you to draw it without having a crossover between the inverting and non-inverting terminals, and it makes the diagram a little bit neater. And then what we do is for an input voltage, we usually draw the input voltage with the most positive voltage on the top. Now in the second way that we draw it, the non-inverting input is shown at the top and the inverting input is shown at the bottom of the op amp. So we flipped it vertically. Now in order to make the feedback work correctly, we have to go to the same inverting terminal. So we get a crossover here between the inverting and non-inverting terminal connections. But the differential voltage that is being connected to the op amp is still shown with the positive voltage at the top. What that means is that on this bottom one here, the positive voltage that you're measuring goes to the positive or non-inverting terminal on the op amp, and that will give you a gain of plus 10. While in this other diagram here, we usually draw it with the positive voltage on the differential voltage being measured going to the non-inverting input. So essentially, between these two diagrams, we flipped the input. So when would we use this second method of drawing? Well, if you've got a single supply op amp circuit that is, let's say, powered with 12 volts and ground, you don't have a negative voltage to output. So thinking of applying 1 volt to the input of the circuit and getting out minus 10 volts just doesn't work. So if you draw it like this, now when we put 1 volts on the input, we would get positive 10 volts out. So in this case, the AV is plus 10 volts, makes some sense. Now, if you have difficulty remembering whether or not a diff amp has a positive or negative gain, what you can do is just jot down some numbers and run through an example, and that will tell you what the output voltage is, and I'm going to show you that next. What you can do is you can just put in some values and work through an example, and then you can figure out what the output is. And you can also use this to justify the gain formula. So let's do an example. Let's say this is 10K for the feedback resistors and 1K for the input resistors. And what I want to do is on the input voltage, I want to put voltages that give me a nice voltage divider. So if I put 11 volts here, then the voltage at this point would be 11 times 10K over 11K. So that's going to be a nice round 10 volts. And then I'm going to put a little bit higher voltage on this one. Let's put 12 volts. So if there's 10 volts on the non-inverting input, if this op-amp circuit is built correctly and you've got good feedback, then the inverting input will also be 10 volts. The op-amp adjusts the output until the inputs are equal. What that means is that now you've got the voltage on both sides of the input resistor RN1 here, and you can figure out what the voltage drop across that resistor is, and you can figure out what the current through that resistor is. So this current is going to be equal to 2 volts over 1K, and that's 2 milliamps. So this current is 2 milliamps. Well, that current can't go into the input of the op-amp because the input of an op-amp is a high impedance. So none of the current goes that way. So that means it has to go through the feedback resistor and find its way to the output. That means that there is 2 milliamps going through this 10K ohm resistor. And that means there has to be 20 volts across that resistor. So now you've got the inverting terminal that you know is 10 volts. And then you've got the voltage drop across RF1, which you know is 20 volts. And from that, you can figure out that Vout has to be minus 10 volts in order to make all that work. It has to be 20 volts below the inverting terminal. So in this case, without even knowing the gain formula, I'm able to figure out that Vout is minus 10 volts. Well, let's punch that into the gain formula and see if it works both ways. So here we figured out using circuit analysis at minus 10. And if I go Vout equals minus 10 times 12 minus 11 volts on the input, V plus minus V minus, this comes out to also minus 10 volts. So there you go. By working through this example and just figuring out the voltages and currents at each point in the circuit, I can figure out what Vout is, and then I've justified that the gain formula is truly minus RF over RN, and in this case minus 10.